Today's lecture is on chapter 5.2 to chapter 5.4 on the valence bond model and hybridization. So the valence bond theory. So covalent bonds are formed by an overlap of atomic orbitals, each of which contains one electron of opposite spin. And so these overlapping lobes must be of the same phase. So if you recall back when we were looking at our individual orbitals, specifically if we look at the p and d orbitals, we noticed that there was one orbital that was a blue color and the other one that was a red color. Okay, and for the d orbitals, you had two lobes that were blue and two that were red. So what these actually are, we neglected to sort of discuss that back when introduced the idea of orbitals, but these are what are called different phase. So overlapping orbitals to form a bond, you have to have electrons that are in opposite spin directions, and then overlap of two orbitals that are in the same phase. Okay, so each bonded atom maintains its own atomic orbitals, but the electron pair in the overlapping orbital is shared by both atoms. So the greater amount of overlap that you have, the stronger the bond. So here we're showing two different 2p orbitals, and we have two electrons here, one of each different orientation. They're going to overlap together to form a single bond between a single covalent bond between these two fluorine atoms. And this single bond where you have a straight ahead overlap is what's called a sigma bond. Okay, and we'll get into um, uh, more detail what the sigma bonds are in upcoming slides as well. Okay, so we can form a sigma bond with a couple different types of overlap. So another type, we just showed two different p orbitals overlapping. You could also have two of our spherical s orbitals overlap each other to form a single bond, which again is called a sigma bond. And so here we can see that both of these are the same phase. They're red in color. These are for two different hydrogen atoms. We have opposite spin electrons. They're going to overlap head on with each other to form the H2 molecule. So that will be a single sigma bond. Okay, again, we can see the overlap of our p orbitals here to form a sigma bond. But we can also have an orbital overlap between an s orbital and a p orbital, as long as they are both in the same phase. So we can say this red color phase for the s orbital, and then we can have our 3p orbital showing the same sort of phase with opposite spin direction. You can see we can form a sigma bond to form the single bond between hydrogen and chlorine in the HCl molecule. Okay, so we have this understanding of the formation of sigma bonds through the direct overlap of orbital. But how do we explain the tetrahedral shape of CH4 using just one s and 3p orbitals? Okay, so if we take a look at carbon and hydrogen. So if we look at our energy diagram for carbon, so carbon again is going to have 6 different electrons in its structure. So if we build our energy diagram, there's going to be 2 electrons in the 1s orbital, 2 electrons in the 2s, and then 1 electron in the first 2 subshells of 2p. Okay, so in order for an electron to undergo bonding, it has to be able to have an unpaired electron to be able to overlap. So in showing this sort of orientation here, it would suggest that, so again, this is for carbon. It's suggesting that there's only 2 specific bonds that are going to be able to take place for carbon. And what we're trying to mimic is the CH4 tetrahedral geometry, where we have a carbon in the center, a hydrogen on top, hydrogen out, hydrogen coming out of the board, and hydrogen coming in the board. Each of these angles having 109.5 degrees. Okay, so how do we orient that? By having a combination of an s orbital, a 2px or 2pz, 2px, and then in and out of the board, 2py. So these are each at 90-degree angles from one another, and then the sphere in the center. That doesn't mimic, so each of these angles being 90 degrees, that 90 degrees between each one does not mimic this 109.5. And also, we only expect two of these bonds to actually form. So there has to be some other explanation at hand that can explain the formation of four equivalent sigma bonds. So what we see here is the formation of what's called a hybrid orbital. So this orientation for carbon is what I just explained up on the board. Okay, so we have two electrons in the 1s, two electrons in the 2s, and then two single electrons in the 2p orbital. But in order to form four bonds, what we're actually going to have is an excited carbon state, where one of these electrons in the 2s is going to be excited up to the 2p. Okay, so that would be a case where you could form four different sigma bonds. But again, those angles that we went through just don't work. So what we have to do now is form what's called a hybrid orbital. And so what hybrid orbitals are is that you combine your s orbital and your p orbitals together to form a larger orbital called a hybrid orbital. So in this case, it's called an Sp3 hybridized orbital. Okay, the 2 outside here is the 2 associated with the energy level for 2s and 2p combining. Okay, so the key aspect of the hybrid orbital is the Sp3. And so what that Sp3 notation means is that you can think of the superscript as saying how many of each s and p orbitals are combined together to form this sort of hybrid orbital. So the s has a superscript of 1, so that means there's one s orbital, and then 3 p orbitals have been hybridized together to form 4 equivalent orbitals, each of identical energy. So let's take a look to see what these Sp3 hybrid orbitals look like. So what we get here, instead of having an s orbital that's a sphere, and then our pz, px, and py suborbitals, which are dumbbells going in the 3 different axes, what we get here are these Sp3 orbitals that take on a shape that sort of mimics a p orbital, but is slightly different. So what we can see here is the blue phase here is actually a much smaller lobe, and then the red phase is a much larger lobe. And so we have 4 for the Sp3 orbital. You're going to have 4 of these individual sort of Sp lobes. And so these lobes are going to orient themselves in which they can put the large lobe of the hybrid orbital as far apart from as they can from each other. So the furthest apart in angle that they can be within a 360-degree space is the same as if we were dealing with a tetrahedral structure. So then one's going to be coming out of the board, and then one's going to go into the board. And so what we're going to have is 109.5 degrees between each of these sp orbitals. Okay, so each of these are sp3 hybridized orbitals together. Okay, so the 4 orbitals each orient themselves 109.5 degrees apart. So if we're trying to form 4 equivalent covalent bonds through this sp3 hybridized orbital, we can now see that each of these different lobes has an unpaired electron of equal energy level. And now you can have 4 different hydrogen atoms, each with an unpaired electron, can now come in and form that sigma bond straight up on each of those different sp3 hybrid orbital lobes. And so that gives us our 3D geometry of the tetrahedral shape for our example species, which is CH4 methane. And so we can see when we, if we're dealing with our tetrahedral parent structure, we can start to remove individual atoms to make these daughter structures of our trigonal pyramidal and our bent shape. And all we have here are that we have a lone pair electron replacing each of those positions. And so these are still sp3 hybrid orbitals that contain either one for the trigonal pyramidal or two different sp3 hybrid orbitals having two different sets of lone pair electrons. And so again, we can see that these hybrid orbitals want to take up more space, which is going to contract that bond angle between the constituent atoms. Okay, so we formed an sp3 hybrid orbital with one s and then one s and then three p orbitals. We can also form what's called an sp2 hybrid orbital. So again, we're looking at our superscript here. So there's a superscript of 1 that's unwritten, so that's 1s. And then sp2 would take two different p orbitals. Okay, so what we have here is now three different degenerate orbitals that are sp2. And then we can have an sp hybrid orbital, which has one s and one p, where you combine the two, and then now we have two degenerate hybrid orbitals called sp. Okay, and it's important to note that for the sp2, we have our one remaining p orbital that's unused, that remains open. And then for the sp hybrid orbitals, we have our two different p orbitals that remain here that are free to accept electrons. So let's take a look at our sp2 hybrid orbitals and see what geometry that we're going to get in this case. So if we go back up on the board and we take a look at our energy diagram, if we have 1s, 2s, 2p, when we hybridize, we're going to, for an sp2, we're going to be taking two different p orbitals and one s orbital. So now we're going to have our 1s, three sp2 orbitals, and then one remaining 2p remaining. So I guess that would be 2 sp2. Okay, so I should write that 1s below. There you go. Okay, so if we're taking a look at our, so again, this is for sp2. So if we're taking a look at our 3D geometry, we are going to have three hybrid orbitals that again are going to take that sort of altered p orbital look where you have one small lobe and one large lobe. And you're going to have three of these degenerate orbitals. And they want to orient in space as far apart as possible from each other within that 360-degree spherical shape. And so we know by our VSEPR theory that those three are going to orient in space 120 degrees apart from one another in this trigonal planar sort of geometry. Trigonal planar. So if we put these orbitals on the side, so if we rotate 90-degree angle, what we're going to see is our orbitals all sort of in a row. Okay, and so it's going to be totally flat if you turn on side. So the important part to note here is we have this remaining 2p orbital. So if we draw this, so if we call this flat here in the xy axis, what we have is our z-axis remaining. And so that remaining 2p orbital can exist as a 2pz. Again, these three here are going to, the three in the equator here are three different sp2 orbitals. So what we have is a remaining 2p orbital, so that's a 2pz. And then we have our three sp2 hybrid orbitals that are all together. So if we take a look back at the slide again, you can see those three hybrid orbitals are indicated by our green, and then we have the blue and red is our pz orbital still shown. Okay, so let's take a look to see how these sp2 hybrid orbitals can undergo bonding. So if we have our 3D shape here, if we have our PZ, and then we have our hybrid orbitals in the middle, and you have two different one of these molecules coming in contact with each other. And then these are sp2s in the middle. So you can get overlap. So if we have opposite spin electrons, we can get a direct overlap between these two unpaired electrons to form a sigma bond. Okay, sigma bond again is a single bond. So we have to remember that you can also have electrons located in your PZ orbitals. So what you can get here is an actual overlap of our PZ orbitals on the top and the bottom. So if I move this a little bit up here and call this the sigma bond, the direct overlap between the the sp2. And so above and below, we have direct overlap of the orbital in what's called a pi bond. Okay, so a pi bond is always going to be an overlap of a p orbital. Okay, pi bond will always be an overlap of a p orbital. And there's going to be two areas of overlap. Okay, whereas a sigma bond is a direct overlap with one area of overlap. For a sigma bond. Okay, so let's look at an example of a sigma and a pi bond forming between an actual compound. So here, if we take a look at the compound C2H4, okay, 2 carbons, 4 hydrogens. If we draw the Lewis structure for this, we find that the answer is a double bond between the carbons and then single bonds between our carbons and hydrogens. Okay, and so we have a trigonal planar geometry, around each of these individual carbons. Okay, so let's see how these actually form by looking at our orbital. So anything that has a trigonal planar geometry, we know it's going to be sp2. So let's take a look at the sp2 hybrid orbitals for each of our carbons. Okay, so we're going to have okay, so if we have our pz orbitals for each of our carbons, carbon and carbon, and then we have our sp2 hybrid orbitals along our equator. So we're going to have a hybrid orbital in the middle, and then we're going to have 2 hybrid orbitals around the equator going further away. Okay, and there's going to be 1 unpaired electron in each of the 3 sp2 hybrid orbitals, and 1 unpaired electron in each of the p orbitals. And we're going to put those electrons in opposite spin notation for the 2 different carbons. And then we can bring in 2 separate hydrogen atoms, and those hydrogen atoms are going to be in s orbital. So these are 2 hydrogens and 2 hydrogens here. Okay, so what we see here is we have a sigma bond, direct overlap between our hydrogen and our carbon throughout the s orbital and the sp2 orbitals in each of these different cases. So we have a sigma bond, another sigma bond, another sigma bond, another sigma bond. So there are 4 sigma bonds between our hydrogen, which is a 1s orbital, and our carbon, which is our sp2 hybridized orbitals. And so now we can see that these sp2 hybrid orbitals along this x-axis here are directly overlapping. And so what that forms is a sigma bond. And then we have 2 electrons here in our p orbitals that are going to overlap above and below, which is going to form a pi orbital. Okay, so you can see we have 2 separate bonds, a sigma and a pi. And so that's going to describe the double bond. So this first bond that we show here is going to be our sigma overlap, and the second one is going to be our pi. And then each of these single bonds between carbon and hydrogen are each sigma bonds. Okay, so that is the formation of C2H4 using the hybridization model. Next, let's take a look at Sp hybrid orbitals. So Sp hybrid orbitals, again, is the combination of one s and one p orbital. And with that sort of formation, you have 2 remaining p orbitals that are present. So if you orient these in space, so the sp orbital now only has 2 lobes, and they're going to orient as far apart in physical space, which again is going to be 180 degrees apart. And so these are going to orient in space just the same sort of way as the 4 different p orbitals did, one along the x-axis, one along the y, one along the z-axis. So what we get here is the possibility for the formation of what's called a triple bond. And so we can have a direct sigma overlap of our sp orbitals. And then you can see we can get pi overlap above and below for one of our orientations. So we'll call this pz. And then you can see we can get another pi overlap in our y-axis for our py's. So we can have 2 different pi bonds, one on the top, one in the equator, and then a sigma bond straight up between our sp hybrid orbitals. So let's draw an example of that sp triple bond. So our example for this is going to be C2H2. So again, if we draw our conformation, our x, y, and z axes, take these arrows off for clarity. Okay, so we're going to have our sp orbital. So this is an sp. So the sp orbital is going to be along the x-axis, direct overlap. So 2 different electrons overlapping here, which we're going to call that a sigma bond. Okay, and then we're going to have our pz's, and then we're going to have our py's. So we're going to see our pz's are going to overlap to form 1 pi bond, and then our py's we're going to see are going to overlap as well to form our second pi bond. And then so the remaining electron So our remaining electrons are going to bond with a 1s orbital from our hydrogen in a direct overlap sigma bond. So our VSEPR theory states that we should have a triple bond between our carbons and then hydrogens located here. And so this takes a totally linear shape, 180 degrees. Okay, so if we take a look at each of these individual bonds, we can see the bonds between our hydrogen and our carbon are going to be sigma. Sigma bonds are always sigma bonds. Our first of our three bonds is going to be sigma. Then one of our second bond is going to be a pi bond. And the third bond is going to be another pi bond. So a triple bond consists of one sigma bond and two individual pi bonds. Okay? So if we talk about when do we expect to see an Sp3 hybridized orbital, when do we expect to see an Sp2 hybridized orbital, and when do we expect to see an Sp hybridized orbital? So what we do is we take a look at the parent geometry and determine what's the parent geometry of the species, and that's the way that you decide which type of orbital you have. If the parent geometry is linear, so we're not talking about the final 3D molecular shape, we're talking about the parent geometry. So if the parent geometry is linear, then you know you're always going to deal with an Sp hybridized orbital, 180 degrees. If we're dealing with a trigonal planar parent geometry, whether the final daughter geometry is trigonal planar or bent, it doesn't matter. You're going to be, if your parent geometry is trigonal planar, then you're dealing with Sp2. If you have a tetrahedral parent geometry, doesn't matter if the daughter geometry is tetrahedral, trigonal, pyramidal, or bent, it doesn't matter. As long as the parent is tetrahedral, we're going to be dealing with an Sp3 hybridized orbital. Okay, so let's take a moment here to have you work through and identify the hybridization at each of the identified carbons in this species. So pause the video and work through this on your own. Okay, so we see this carbon here has four different bonds coming off and it carries this tetrahedral shape. And so since it's tetrahedral parent geometry, that means that it has to be Sp3. So this carbon here is Sp3 hybridized. This carbon here, since it has three areas of charge density, that's going to have a trigonal planar parent geometry, which means that that has to be an Sp2 hybridized orbital. And this third carbon here on the far right, again, has 1, 2, 3 areas of charge density or of areas of electron clouds, which means it's a trigonal planar parent geometry, which again means we are Sp2 hybridized. Next, let's take a look at this structure here. And so here we don't have the 3D dashes and wedges, so you should be able to recognize based on how many areas of charge density to determine what is going to be the hybridization at each of our carbons and each of our oxygens that are attached to hydrogens. So we're looking for 1, 2, 3 carbons and then 1, 2 oxygens. So pause the video and work through that. Okay, so the carbon on our furthest left has 1, 2, 3, 4 charged clouds, which means it's a tetrahedral parent geometry, which means we are Sp3 for the far left. Our carbon in the middle, again, we have 1, 2, 3, 4 areas of electron clouds, so that's tetrahedral parent geometry. Therefore, again, that's Sp3. The third carbon on the far right, we have 1, 2, 3 areas of electron clouds. So therefore, we have a trigonal planar geometry, which means that we are Sp2 hybridized. Now, if you work through the proper Lewis dot structure and the VSEPR theory, you should see that each of these oxygens here are going to have two sets of lone pairs associated with them. So this oxygen here and this oxygen there. So two sets of lone pairs included with the two different sigma bonds here, we're going to see 4 areas of electron density or 4 charged clouds for each of these different oxygens, which means we are a tetrahedral parent geometry, even though our overall shape is bent. So tetrahedral parent geometry means that we are Sp3 hybridized for both these oxygens. All right, our final slide, taking a look at a ball and stick model, we can see here. So pause the video and identify the 3 carbons that are highlighted. Okay, so our furthest on the left, we have 1, 2, 3, 4 bonds coming off it. So that's tetrahedral parent geometry, therefore sp3. Our second carbon here has 1, 2, 3 charged clouds coming off of it. So therefore it's a trigonal planar parent geometry, sp2. And our third carbon here has 1, 2, 3 coming off. Therefore, it's trigonal planar parent geometry, and therefore sp2 hybridized. All right, that's it for today. Thank you.